should I share my screen or?
Yes, go for it.
You can do that.
Okay.
Okay, so we are live.
So can you see it now?
Yes, yes, yes.
Okay, Atul, so you can introduce him now.
Yeah.
Should I share my screen or?
Yes, go for it.
Yeah. So good afternoon, everyone. It's our great pleasure to introduce Shishuo Fu for the special functions and number theory seminar today. So I know Shishuo since long time, since he was a PhD student at Penn State with George Andrews, and we have met at a number of conferences in person and now online. So Shishuo works mainly in combinatorics and also in number theory. And today he'll be talking on bijective recurrences for Schroeder triangles and Comtet statistics. Over to you, Shishuo.
Okay, thank you. Thank Graf Adu for the invitation. I feel very honored to speak at your seminar. This is, I mean, actually my first talk in India, even if it's virtually. I really wish one day I could come to India to see your beautiful country. Okay, anyways, so my talk, so in Graf's email, he said there's not much restriction, just that I have to include something for non-expert. So I know this is a seminar for special function and number theory, but I'm sorry, maybe my talk today doesn't have much to do with special function or Q series per se, but it's mainly combinatorial, but I can say it's number theory flavored. Okay, all right, so I will begin by explaining the title. So I will first introduce you what is I mean by Schroeder triangles. I will begin with a few examples with classical triangles considered by enumerative combinatorics. And then I will explain this concept is new, Comtet statistics. I will explain this later. This is joint work with Zhichong Lin and Yaling Wang. Zhichong Lin is a professor at the Shandong University, and Yaling Wang was previously my master student. Okay, here we go. So this is the plan for the talk today. As I said, I will begin with introduction and I think enough motivation. And then the major part is I will explain after we see one bijective proof for the recurrences enjoyed by this Schroeder triangle. I will shift the focus to tell you what is separable permutation, and I will talk about how we can achieve similar combinatorial bijections on separable permutations instead of shorter passes. And the second part is I will talk about what we mean by Comtet statistics. We introduce a new permutation statistics. And then in the end, if time permits, I will briefly mention some ongoing and future work. Okay, so let's begin with very classical things. This is Pascal triangle. Everybody knows this, I suppose. We begin with binomial theorem. You have this binomial theorem, you expand and you get coefficient for each term. And when you plug in special values, like the most natural thing to do, you plug in x and y equal to 1. Then you get this identity tells you the power of 2, the 2 to the n, is the sum of all these binomial coefficients, n choose k. So when you align these binomial coefficients in a triangular array fashion, that means for n choose k, we put it in the nth row counting from top down, and the kth column counting from left to right. You get this famous Pascal triangle or Pascal array. But actually in China, we call it Yang-Hui Sanjiao. Yang Hui is a Chinese mathematician long time ago, and the Sanjiao is the Chinese for triangle. And I also Googled a little bit. I Googled the binomial theorem, there will be some names popping up, and I see one Indian name in Ghana. I don't know if I pronounce it right, but I guess maybe in your culture, you also, in your history, you also attribute this to your Indian mathematician, I guess. Although Western cultures call it Pascal triangle. Anyways, so this is the Pascal triangle, the very classical thing. When you sum up the row, you get 2 to the n. And for another example, we can consider also a very classical example in combinatorics, also number theory, is the so-called Eulerian polynomial, first studied by Euler. You have a permutation of n letters, and you count how many descents you have. For descents, we mean if you write this permutation pi as pi 1, pi 2, pi 3 from left to right, whenever you notice 2 consecutive entries, pi I is larger than pi I plus 1, this pair, you call it a descent pair. And then you count how many pairs you have. Suppose this permutation gives you k descent pairs. Then we collect all such permutations of length n with k descents, and we denote this number n choose k, but with this angle parenthesis. So this is the so-called Eulerian numbers, but don't be confused these numbers with another famous number called Euler number, which is tangent and second number. Okay, so this is Eulerian number. So if you consider the Eulerian polynomial, that's simply the generating function for this Eulerian number. Okay, this we usually denote it as a sub nt. And this also gives you naturally, just like in the case with the Pascal triangle, triangle, which we can call it Eulerian triangle. So you see, it shares some nice feature with Pascal triangle. For example, it's palindromic. That means when you read each row, left to right and the right to left, it's the same thing. Right? We call it palindromic. And when you sum up the rows row-wise, you get, of course, the factorial number, because that's how many permutations you have, right? Okay, maybe just one more example, also famous in combinatorics, the so-called Bell numbers and the Stirling numbers of the second kind. So Bell numbers, combinatorially, it counts how many set partitions. It's not integer partition, it's a set partition. Given a set of n elements, you partition it into a non-empty subsets, and you count how many subsets you have. And this refinement give you a big S and K. That's the set partitions of n with exactly k subsets. So they sum up to give you the Bell number. And another way to introduce the Stirling numbers of the second kind could be this way. You consider, say, 1 x squared x cubed, all such monomial, and another polynomial you consider this q sub k q following factorial. Both of them give you a natural basis for the vectors of polynomials of degree less than or equal to m. And then you consider what is the transition matrix, right? Whenever we have two bases for a linear space, we consider the transition matrices. So when you expand the standard basis in this x sub k basis, this coefficients give you exactly the Stirling numbers of the second kind. And we also have such a array, triangular array. And when you sum up, this gives you.
Won't you have some minus signs if you use falling factorial?
Stirling numbers don't, second kind don't have minus, but usually the Stirling numbers of the first kind usually referring to combinatorially, that's the number of permutations into k cycles. And then for that, it usually has minus signs, alternating minus signs. And we can forget the minus sign and introduce the so-called unsigned Stirling numbers of the first kind. But for second kind, we don't have minus signs. For example, you can try x squared when n equal to 2. And when you expand x squared in this basis, in this basis, you have x and x times x minus 1, right? So you get x squared minus x, then plus x. So that gives you back exactly x squared. So that means the coefficients are 1 and 1, right? So are we good?
Okay, thank you.
Okay, no problem. All right. So I think that's enough examples. So what I'm trying to tell you with all these classical examples is in enumerative combinatorics, when we study sequences, we usually, it's typical to study some refinement of such sequences so that you have, instead of a single sequence, you have a triangular array. And usually that will lead to deeper understanding of the sequence you are interested in. So now let's come to our subject today. So we begin this sequence, the so-called Schroeder numbers, sequence of Schroeder numbers. According to a paper by Richard Stanley in applied, published in the Mathematics Monthly, this turns out to be a very classical sequence because in this Moralia, the table talk section from Moralia, which is written by Plutarch. Plutarch was a Greek philosopher, historian, biographer, famous for another work called The Parallel Lives. Actually, I did a little bit about this Parallel Lives because it sounds interesting. It somehow is like the bijective combinatorics we do today, right? Because when Plutarch write this Parallel Lives, he connected 48 noble persons from Greek and the Roman, and he paired them into 24 pairs, like one-to-one correspondence, so that he explained their story, their life story. They have some sharing features between this pair. Okay. So anyways, in this Moralia, here's the paragraph taken from this Moralia. You can read it. So Hipparchus person, certain person, he actually refuted some claim by Chrysippus, saying that the compound propositions exceeds a million, but actually he gave a very precise answer to be actually 103,049, a little above 103,000, much less than a million. And then there is another number. Okay. So the number I color here is actually turns out to be one of the entries. Actually, I guess the 10th entry in the sequence of little Schroeder numbers. So just like the Stirling numbers, we have first kind, second kind. For Schroeder numbers, we also have the so-called large Schroeder numbers and the little Schroeder numbers. So if you want to get to know more about these two sequences, you can refer to the online encyclopedia of integer sequences. Here is their entry. So actually, aside from the first entry, all the large Schroeder numbers are precisely twice the little Schroeder numbers. So here are some references. So a serious study of these Schroeder numbers began by a German mathematician Schroeder. Because that's why it's called Schroeder numbers. Okay, naturally. I don't know how to read Schroeder, but I guess this means 4 combinatorial problems. So in his paper, Schroeder considered the second combinatorial problem is the answer to his second combinatorial problem is exactly given by this little Schroeder numbers. So here's a picture of Schroeder taken from Wiki. Okay. So actually, there are many combinatorial interpretations for these two sequences. For example, in Schroeder's original paper, he considered the so-called word bracketing problems, how you can, given a word consisted of some alphabets, how you usually just one alphabet, how you can add a pair of parentheses or brackets properly. He asked the enumeration of such ways. So that the answer was given by little Schroeder numbers. And also more geometrically flavored is this Schroeder passes. You consider your pass contained in this first quadrant from 0, 0 to 2, and 0, consisting of 3 kinds of steps, up steps, or you can think of it east to north steps, going upward and to the left, to the right, 1, 1 direction, or downward, or horizontal. But horizontal, you cover 2 unit steps instead of 1. But if you cover 1, 0, that gives you the Motzkin numbers. So that will give you large Schroeder numbers. If you put remember, little Schroeder numbers was just half of the large Schroeder numbers. So you need to put some restrictions. So if you restrict that, there is no horizontal step along the x-axis, you get exactly the little Schroeder numbers. And also there's a notion of separable permutations, or in terms of pattern avoidance, it's 2, 4, 1, 3 and 3, 1, 4, 2 avoiding permutations. I will explain this terminology momentarily. And actually, in terms of pattern avoiding permutations, there are more than 1 interpretations. Here are also 2 counted by 2, 4, 1, 3 and 3, 2, 1, 4 avoiding permutations, and 8 other pairs. And also something a little weird like this, avoiding these 2 patterns and one of the patterns among these 5 candidates. And also plane trees and polygon dissections, and 0 to 1 avoiding inversion sequences. Inversion sequences is also called lemma code. It's a nice way to encode permutations. And 0 to 1 avoiding is putting further restrictions on normal inversion sequences. So here I will give you the definition of pattern avoiding permutation. A permutation pi is said to avoid a certain pattern tau if there exists no subsequence of pi that is order isomorphic to tau. For example, 3, 1, 4, 2, 5 is said to avoid the pattern 3, 2, 1 because you cannot find a subsequence, say ABC with A larger than B, B larger than C. But it does contain 1, 2, 3. 2, 1, 3. For example, 3, 1, 4 give you a subsequence of 2, 1, 3, a pattern of 2, 1, 3. Okay. So in our talk today, we will focus on these 2 models, Schroeder passes and the separable permutations. And by the way, one of the major reasons why people are interested about this pattern avoiding permutations, at least their interest at least dates back to Knuth. Donald Knuth considered with some stock sorting permutations originating from computer science, he actually proved that whenever you choose your pattern to be a length 3 pattern, there will be 6 different length 3 patterns, and you avoid them. And this enumerator, the enumeration was given by exactly the Catalan numbers. Hence Catalan numbers. This is a famous result in pattern avoidance. Okay, and we say 2 patterns are Wilf equivalent whenever they are equinumerous, the 2 subsets given by the avoidance of these 2 patterns separate respectively. They have the same cardinality, and then we call they are Wilf equivalent. That was because Wilf was the first one to raise such a question to study this kind of topic further. Okay, so so now we know our sequence. We're gonna study the Schroeder number, the sequence of Schroeder numbers, more precisely large Schroeder numbers. I think also the little Schroeder numbers as well. So what is the array? How do we refine the sequence to get the triangular array? So this is how we do it in terms of Schroeder passes. We consider a peak on the Schroeder pass to be a consecutive 2 edges, one going up, one up edge, then immediately followed by a down edge. This is graphically, this is easy to understand why this is called a peak, right? And we talk about the height of the peak. The height of the peak is the y coordinate of the middle point, or you can think that the highest, the summit, the y coordinate of the summit. So all the peak at height 1 will be called a hill for short. So when you refine your counting of shorter passes by the number of hills, in other words, we let R and K to be all the shorter passes of lengths 2n. Remember, shorter passes we always give you a pass of even lengths because we go up and down. Each up and down comes in pair, so that gives you 2. And then each horizontal step contributes a length of 2. So eventually you sum up, you always get an even number, right? So we call R and K. We use R and K to denote the number of shorter passes of even length 2n with precisely K hills, peaks at height 1. And respectively, we use S and K to denote the number of little shorter passes of length 2n with K hills. Then refining like this, you get precisely these two triangular arrays as I have shown here. And they also have the corresponding OERS entries you can refer to later. So if you stare at this long enough, you might be able to notice some rules that you can generate lower rows from upper rows, just like the way Pascal triangles goes, right? Pascal triangle, each entry is the sum of the entry above it and the entry above it and to the left, right? That's the general, that's the classical recurrence relation for Pascal for binomial coefficient. So if you, like I said, if you stare long enough, you might be able to notice such a pattern going on. For example, this 11 can be thought of as generated from 1 times 3 plus 2 times 2 plus 2 squared times 1. And you can go on, but then after that, this will be 0. So essentially, you only get a finite summation. And also here in the second array, you get this 26 can be generated from 2 times 4, 2 times 3 times 0, 2 times 3 squared times 1. Notice that we skip 6 here, so the sequence starts from here, starts from 4. And this is not by coincidence. This is true in general. So these two triangular arrays obey such recurrence relations, like we put up here. So for the first triangle, which sums up to be the large Schroeder numbers, you have these two recurrence relations. Notice we have, for each triangular array, we have 2 recurrence relations, because when you get the number in the first column, the rule is different from when you get the number for other columns. Okay? Because for the first column, you do not have an entry above it and to the left, because this is the border. This is the border column, right? So the rule will be a little bit different. Like here, you don't have this entry for the first rule. And similarly, for the second array, we also have such a nice recurrence relation. So our first goal today is to give combinatorial proof of such recurrence relations. But before that, we can also briefly mention what is the more or less standard proofs, algebraic using generating function and stuff proofs. Okay, this is how the standard proofs goes. We have such a notion of so-called Reorder arrays. Reorder arrays is the huge generalization of Pascal triangles, for example. One way to define it is you have a infinite lower triangular matrices. You consider all the column generating functions. You take each column using it as coefficient. You compute the generating function, right? When the generating function behave like this, the first column give you gx, the second column give you gx times fx, the third column gives you gx times fx squared. In other words, the column generating function behave like geometric series. Right? You have each consecutive column generating function has this constant ratio. If that's the case, then this triangular array is called Reorder array. Of course, we have some further conditions. The Gx must have non-zero constant term, and Fx has zero constant term but must have non-zero linear term. Usually, we take this leading coefficient to be 1. This is so-called the standard Reorder array. Anyways, so in the theory of Reorder array, here is another an alternative characterization, not using column generating function, but using what we have observed here, such recurrence rules. So, like you can see here, Rni, which is the entry in this Reorder array in the nth row ith column, is generated by the such entries above it with certain coefficients. And also the first entry, the first column, we usually denote the first column by the zeros column. The rule is a little bit different. You have one less term. So whenever you notice this rule holds for all entries, that means this constant, this coefficients here, this linear coefficients here are independent of the entry. They stay the same. For example, in the Pascal triangle case, that will be exactly 1 and 1, always 1 and 1. 1, 1, and then infinite many 0, if you like. Then this is also gives you Reorder array. So such characterization and the characterization given by column generating functions turns out to be equivalent. That means once you have, for example, you have generating function on one hand, and then you can generate what are these sequences. We call it A sequences governing the first rule and Z sequences governing the second rule. That's one direction. Another direction you can go is you are given such A sequence and the Z sequences, you can of course automatically generate all the arrays. Then the generating function, the column generating function will behave exactly like this, and you can compute the generating function. So essentially what the machinery behind all this correspondence is essentially Lagrange inversion. But the theory somehow give this in a compact form so you can utilize very conveniently. But the essential idea is a Lagrange inversion. So here, if we take this approach, because we can easily show the column generating function for these two triangular arrays, namely the first array for the large Schroeder number, the second array for the little Schroeder number, they behave like this: gx times fx, gx times fx squared. This is simply because, remember, the array is refined according to the number of heels. So actually the number of heels divides your Schroeder path. For example, you have key heels. Then this key heels naturally divides your Schroeder path into k plus 1 components, right? You just view each component between consecutive heels. It's a Schroeder path without heels, right? So Schroeder path without heels is generated by the first column, which means k equals 0. So that's exactly gx. And then there will be k plus 1 copies. So that explains why the generating function behaves like this geometric series. So anyway, that's a standard machinery, standard approach to prove this kind of thing. You compute the generating function, and the generating function, according to the theory of Reorder array, will generate for you the A and the Z sequence, and the A and the Z sequence are exactly what you expected here. This blue color and the red color coefficients. So that's not difficult and very standard. But combinatorially, that's how we do it. That's not how we do it. But why do we care? Why do we search for combinatorial proofs? So let's listen to the master, shall we? So Schroeder advocated that every algebraic relation is to be given a combinatorial counterpart and vice versa. So we should do that, right? Because master tells us to do that. So I include two pictures with happy smile of Schoenberg. For example, the large Schroeder number satisfies this recurrence relation, not the triangular array, but the large Schroeder number themselves. So in the literature, there are at least two different combinatorial proofs given. First one by Falta and Zerba, and another by Sulek. They use different, I guess, a little bit different models. Falta and Zerberger use well-weighted binary trees, and Sulek use shorter passes, elevated shorter passes. So Sulek's approach is closer to us because we use shorter passes. Okay, so let's recall these recurrences in this slide. So the key idea is we have to explain what this 2 to the j minus k power and what is this 2 times 3 to the j minus k minus 1 power. What are they doing combinatorially? That means they are giving you some not one-to-one map. It's like 1 to 2 to the j minus k copies map, right? So that gives you the basic idea. And notice the thing here is, for example, for Rn0, that means you have no heels, 0 number of heels. And here you have j heels. So you have to somehow delete heels, efface heels. And on the other hand, there are multiple ways to do it. And it better behave like 2 times some 2 to some power. Okay, so let me show you the main idea. I will skip the details because time that does not permit. So the main idea is, like I said, on one hand we have to eliminate get rid of all the extra heels. So the idea is to elevate the pass, because here are all the peaks at the height 1, right? You make the height bigger, you make the heel disappear. That's very natural. But then how to explain this 2 to the power of j and 2 times 3 to the power of j minus 1? The basic idea is, for the first case, for each peak, we have a choice to either keep the peak as it was, or we make the peak upside down. We flip the peak. So this peak become a valley in some sense. So there are two choices. So that gives you why you have 2 to the j, because you have j heels, right? After you elevate the pass, this j heels will be, of course, peaks at height 2, because you elevate the pass. Then this height 2 peaks, you can choose either to keep it the way or you flip it. So that's the main idea. But there's some technicalities to be taken care of, because, for example, here, for this heel, it's at the border of the elevation, the point where you elevate, where you insert at the very left and up here and up edge, and at the very right down edge. That's where you elevate the pass. But at this border, when you choose to flip down this heel, you get a heel, right? By elevating, you get rid of the heel. But by flipping, you get yourself another heel, right? So that's a trouble, right? We don't want heel. So we have to take care of that. And in another case, for explaining the coefficient 2 times 3 to the j minus 1, you have 3 different choices, right? Because now it's 3. So you can either keep it the way it was, flip it, or flatten it to be a horizontal edge. But again, this will cause some trouble in some special case. For example, if you have 2 consecutive peaks and you choose at the same time simultaneously flip them. When you flip them, this will give you a new heel here, right? So that's a problem. So we somehow taken care of this by introducing the M basin. So that means when you take a string of peaks, consecutive peaks, and you decide to flip them all, you do not actually do that, but you get a basic somehow sort of put down all these hills, right, to make it all the horizontal lines on the x-axis. Anyways, that will be the details. So that's the main idea. You make these choices, either 2 choices or 3 choices, and taking care of all the problematic cases. I mean, there's some technical things, but it can be done. Yeah. Anyways, so that's done. So we were able to show this bijectively. Why this recurrences holds. So that's our first result. Then this result raises several natural questions. First of all, because we noticed that there are other combinatorial models counted by large Schroeder numbers. For example, separable permutations. Remember the 3142 and the 2413 avoiding permutations. Then can we use separable permutations to similarly explain that recurrence relation for the triangular array, Schroeder array? So that's our first question. But to do that, you have to first find the appropriate statistic to refine your separable permutations so that you get exactly the same array, right? So that's our first goal, to find such a statistic defined on separable permutations to give you R and K. And we find it, and we call it initial ascending run. And I should make a remark that this turns out to be not the we are not the first person to define this statistics. It already exists in the literature by a paper by Kitaf, Clayson, I guess, and their collaborators. Yeah. And they have a different name for it also. Yeah. Okay. Then once you find this statistic, can we successfully explain using this new statistic, explain in a similar way the recurrence relation combinatorially? Ideally, we can find a bijection from Schroeder passes to separable permutations, such that the number of hills, remember that's the K in the Schroeder pass case, will be transferred to this new statistic, namely IAR, initial ascending run. But unfortunately, the known bijections from Schroeder passes to separable permutations in the literature are not easy, to say the least. They are usually combination of several bijections, so which will make the understanding of this statistic transferring a little bit difficult, to say the least, I guess. So I didn't do that directly bijectively, but we do it recursively. In other words, we were able to, relying on the model of separable permutations, using this new statistic IAR, we were able to do the same thing as we did on the Schroeder passes. We combinatorially explain why these recurrences hold in terms of separable permutations. And the third question is once we have this actually not so new, but anyway, this statistic we find, can we apply it to other known results about separable permutations and hopefully refine some known results? And we also did that. Okay. And here's another remark. Yeah, so another model, which I briefly mentioned several slides ago, the 0 to 1 avoiding inversion sequences can be also refined to give this triangular array. And the refinement is also very natural. The statistic corresponding to IAR, in this case, will be the number of initial zeros. So you have your inversion sequences. Just count how many at the beginning, how many zeros you have. That will give you the K. Okay. So this result will be given, will appear. Actually, this paper is already accepted. It will appear soon. Yeah, like I said, this statistic was already previously studied by Clayson and Kitaf in 2008, and they call it the leftmost initial run, I guess. So LIR for short. So one thing to notice is actually another way to view, alternatively way to view IAR. Oh, actually, sorry, I didn't actually define the IRR yet, right? So IRR is when you have a permutation, you just judge by the name, right? Initial ascending run. So you just count from the beginning, from left. That means how many consecutive ascents you have. Pi 1 less than pi 2 less than pi 3, all the way up to pi I. Then the next one will be pi I larger than pi I plus 1. You have a descent. Then you make a cutoff here, and you count how many entries you already covered. That will be IAR. And when for the identity permutation, namely 1, 2, 3, all the way to n, it doesn't have any descents. The descent number is 0. So in that case, we make the convention that the IAR number is n, the largest one. So alternatively, another way to view this statistic IAR is you can think it's actually the smallest descent of pi. Remember, because this is the first time you encounter a descent. So when you consider the set values statistic, the descent set, that means you collect all the indices of the position where you have your descent. Let's give you descent set. Then the descent number is the cardinality of the descent set. And IAR is the smallest entry of the descent set. So in other words, once you determine the descent set, that will automatically imply the IAR as well as descent. Okay, so I will make this remark here because later we will come back to this remark. So now if we let P sub nk to denote the set of permutations of length n, again, because it's separable permutation, so it's 2, 4, 1, 3 and 3, 1, 4, 2 avoiding permutations. And the number of, the IAR statistic is exactly K. You collect this subset, and its cardinality is P and K. Then it turns out this P and K satisfy precisely the same recurrence relation, but with shifted initial value. So that's why we have Rn minus 1, K minus 1 equals P and K. So we were able to, like I said, bijectively show these recurrences 7 and 8. So the model, we cannot use permutations. Permutations, doesn't have this geometric intuition that will help you, that will guide you to discover your bijection you need. So we switch to another model, which is in natural correspondence with separate permutations. You have to introduce 2 standard operations on permutations, namely the direct sum and the skew sum. Do I have? Yeah, I have an example here. So 1, 2, 3, O plus or direct sum with 2, 1 is 1, 2, 3, 5, 4. Essentially, what you do is you take your second permutation sigma and you lift it up or you raise it up by exactly how much? By exactly the length of pi. And for skew sum, you instead you lift up your first permutation pi by exactly the length of the second permutation sigma. Okay, for example, 1, 2, 3 skew sum with 2, 1 is 3, 4, 5, 2, 1. So using these 2 operations, we can generate from 1, just the permutation of length 1, the 1, we just use 1 as the starting atoms, and these 2 operations, O plus or O minus, we can generate all the separable permutations. Actually, that's another way, equivalent way to define separable permutations. In other words, separate permutations, exactly those can be built from permutation 1 by applying these operations O plus and O minus repeatedly. So once you have this expression of permutations in terms of O plus direct sum and skew sum, it naturally corresponds to this so-called disk trees. Yeah, you just take the let me see. Do I have an example? Okay. Yeah, sorry, I didn't put example here. But for example, let me think. For this one, okay. We can further write 1, 2. Yeah, how about I do the other way around? For example, I take this disk tree. This root O minus means this root here means everything to the left will be larger than everything to the right, right? So I can add a leaf here. So this leaf will be the smallest. So this will be 1. This will be 1, and then here I have the number of nodes is 1 fewer than the number of entries in the permutation. So here we have 3 nodes in the tree. So it will correspond to a permutation of length 4. So we put 1 here, and then this is O plus. So that means everything to the left will be smaller than everything to the right. So here we must have 3, actually 4. 4 is the largest one in the remaining 3, 2, 3, 4, because 1 we already used, right? 1 is here, so 4 is here. Then here is 3, 2. So this tree corresponds to 3, 2, 4, 1. Okay, so this correspondence is easy to understand, I guess. Anyways, so on this disk tree, so the disk tree has this subtlety, I think, about the right chain condition. The way we define it, it has to satisfy this right chain condition. That means any maximal chain extending to the right. That means you start from some node and consider its right child, then its right child, then its right child. You always go to right. You get a right maximal chain, right? This chain must alternate in the sign, in the label. In other words, it either starts with O minus, then O plus, O minus, O plus, O minus, or it starts with O plus, then O minus, O plus, O minus, like that, right? So once we're given a sequence of label, for example, this is a sequence of label minus, plus, minus. There are more than one way to make this tree, right? All these 5 trees shown here give you exactly this label sequence. The order we read this label is the so-called in order traversal. That means whenever you have a chance to go left, you go left. Then you go to parent. Then you go to right subtree. You go deep first. This is deep first search. Okay, and you traverse all the nodes. You get a label sequence. So as you can check easily, all these 5 trees give you the same label sequence, minus, plus, minus. But among these 5 trees, only the first 4 are the disk trees we define. Disk trees is the direct skew tree for short. Because the last one doesn't satisfy this right chain condition, because you have minus, minus here, right? Okay, so anyways, that is a model for our disk tree. So there was we proved in our earlier work in 2018 that there is a bijection between the separable permutation and the set of disk trees with n, here should be with n minus 1 nodes, because the number of nodes is smaller than the length of the permutation. And it has this nice correspondence between the statistic. The descent set corresponds to the index of the nodes labeled O minus. So we will rely on this bijection to transfer our problem from the Schroeder, from the separable permutation to these disk trees. Then we were able to prove the thing we want bijectively. Let me see. I guess I still have 10 minutes, right? I guess I have to speed up a little bit.
Sure.
Yeah. Okay, so now come to the second part, second unknown thing in our title, the Comtet statistic. Because now we introduce this IAR statistic. According to our results, its distribution among all the district trees were given by exactly the distribution of this statistic called components. So components, the way to define these components is also using the direct sum. So now you are only allowed to use direct sum, not skew sum. You are already allowed to use O plus. So you can decompose your permutation into several components connected by this O plus, and you decompose all the way you can until you cannot decompose any further. So you count the number of components. That's the maximum number you can have, right? So that maximum number is called the component number of pi. So it turns out this component number of pi was first studied by French mathematician Comtet in his famous textbook, Advanced Combinatorics. And when you consider the so-called indecomposable permutation, that's permutations with component number 1, only one component. It has this nice, interesting generating function given by Comtet. Actually, that was an exercise in his book. So that's why we call any statistic equidistributed with component number to be called a Comtet statistic, just like when we name Eulerian statistic and the Mahonian statistic. Okay, so by a previous result, this component statistic on the permutations corresponds to this component S on the path, and component S on the path turns out to be precisely the number of hills plus 1 on the shorter path. So that's convenient for us because now we already know the number of hills on the shorter path corresponds to the IAR, the initial ascending round number on the separable permutation according to our results. So then we combining Clayson, Kitaf, Sten-Grimson's results with our result, we get corollary that IAR statistic and the component statistic, they have the same distribution on separable, on the set of separable permutations. One thing to notice is they are not equidistributed over all symmetry group, over all permutations, because as you can see, if you add in for n equal to 4, if you add in the missing 2, because these two are avoided, right? These 2, 2, 4, 1, 3, and 3, 1, 4, 2 are avoided. So now if you add them back, they give different distribution. This one give you 2, 1, this one give you 1, 1 for component. So I guess that's partially the reason, maybe we think that's partially the reason why this statistic doesn't attract much attention in the literature, because they are not equally distributed on the entire set, but on this particular subset. But we are somehow fortunate to notice this connection. So we have some further results because by a paper by Kim and Lin, one of our collaborators, in this paper, they get this result. These 4 pairs, when you consider pattern avoiding permutations according to these 4 respective pairs, you have this distribution. And when I put subscript des or des here, means this distribution is even true when you refine it by the decent number, or here by the decent set. Recall that I made the remark earlier that decent set dictates decent numbers and dictates IAR. So once you have decent set equidistribution, you get IAR equidistribution for free. But for these 2 pairs, it's not true for the set valued equidistribution. It's not true anymore. So we have to work further to get this result. And after their paper, a follow-up paper by Wang, adding one more refinement by the double descent DD. So we were able to add yet another statistic, our statistic IAR, into this equity distribution. To say this precisely, that means we have on one hand a separable permutation, namely 2, 4, 1, 3, 3, 1, 4, 2 avoiding permutation. And on the other hand, 3, 4, 1, 2, 3, 4, 3, 1, 2 avoiding permutations. They have exactly the same distributions according to the number of descent, the number of double descent, the number of IAR. Okay, so this result further refined Wang's result and the Kim and Lin's result. But this result, we couldn't prove it bijectively. We have to prove it algebraically. Basically, we consider this trivialized generating function with corresponding to these three statistics and solve a nasty functional equation. We have to use Maple to solve it. It's not doable by hand. But anyway, we can solve it algebraically and prove this thing algebraically. Okay, I think I have a little more thing to say. So in our recent joint work, we consider not on separable permutations anymore, but on those subsets counted by Catalan numbers. Remember I said when you avoid one pattern of length 3, you always get the sequence counted by Catalan numbers. So for example, you consider SN321, all the permutations avoiding 3-1 patterns. By these three Israel scholars, Adin, Bagnon, and Rochman, in this 2018 paper, they consider 3-1 avoiding permutations according to, I guess, statistics comp and IR, because of course they call IR using a different name. They prove they are equidistributed. Then Ruby, also from Vienna, Ruby was able to refine this, to actually strengthen this to the jointly symmetric distribution. That means adding Bagnon and Rochman, they can only prove IR is equidistributed with comp. But Ruby extends this to be equidistributed with IR comp, then you switch the pair, comp IR, they are the same. And including this set value statistic left to right maximum. Ruby proved it using dict passes. So we were able to prove it using just the permutations and some other companion results. For example, on 3-1-2 avoiding permutations, we can also have this nice equidistribution result where IR and comp are jointly symmetric distributed, and you can add in the L max and the descent basis. And also on 1-3-2, we also have these results. And also on these separable permutations, again, on these separable permutations, we can also prove this equidistribution result. And this one appears in a recent preprint. This one, we were able to prove it bijectively. So this one, I think is really nice because we prove it bijectively. And this one, this result, number 4 result, reduces to number 2 and I guess, yeah, reduces to number 2. And we also use the model of disk trees. And we have some also some generating function results. You consider this trivariate generating function. We computed their order. The order turns out to be rational, the generating function. And some of them has further symmetry properties. I don't have time to go over. And this is one picture showing the main idea of the proof. Basically, you start with something here, and you have to kind of doing a surgery to the tree. You cut something, you shift it down, then you cut, you shift down, you cut, you shift down, and eventually it comes to this dotted region here, and then you do some further thing, the step 2 here, to make it right, and to get the idea, to get the bijection down. Again, that's the main idea, and I give you one picture to show you the idea behind this. It's the Leuden crater, the so-called Leuden crate or crater. It's kind of the energy will be transferred from the rightmost ball to the leftmost ball one by one. So that's like our bijection. Our bijection is doing surgery on this tree. You shift something above here and along this path down all the way down to here, and you do something here. Yeah. Again, there are many details about this bijection. I'm sorry, I do not have time to cover. I will end by briefly mentioning some future work and actually ongoing work. How about equidistribution of these two statistics? Because we already witnessed several results. Remember on 312 avoiding permutation, 321 avoiding permutation, 132 avoiding permutation, and also separable permutations. All of them, IAR and comp turns out to be equidistributed. And actually all of them turns out to, the stronger symmetry distribution turns out to be true. That's somewhat surprising to us when we first noticed this. And then we consider over other subclasses like pattern avoiding permutations where you avoid two patterns of length 3 and maybe one patterns of length 4 and the other two patterns of length 4. In other words, there are many things to do if you want to do this because there are many different patterns to consider. And then another interesting is getting back to this tree model. Remember, we have this in order to traverse the tree. Whenever you start with the left subtree and then the parent and then the right subtree. If you have a universal tree, I mean, the tree without labels, what I mean is tree without labels. When you traverse this tree, it doesn't make much difference the way you traverse it. But now our tree is discrete tree. That means our tree has labels. And this label has this non-symmetric right chain condition. Remember, for the right chain, the label has to alternate. So that means when you consider different tree traversals, in theory, this should give you different kind of enumeration problems. So that's exactly what we did in our recent preprint, in this preprint, I guess. Essentially, you can consider all 8 different ways to traverse the tree. I listed them all here. And then you can consider similar statistics corresponding to IAR. IAR is like you count how many initial, when you traverse the tree, you sort of make the order along these labels, right? You have the order of the labels. So you consider from the smallest label, initially how many black dots. Black dots here means the O+. Initially how many black dots you have. Then you have a statistic. So 8 different ways to traverse this tree. Then you have 8 different statistics. So somewhat surprisingly, it turns out we have further equidistributions among these 8 different things. At least some of them here. We have this very nice equidistributions. I guess that's it. I think I will stop here. And just to pretend I'm actually there at your university. I searched for a picture of your university. Okay.
Thank you.
Okay. That's all. Thank you. Any questions?
Yeah, thanks very much for an interesting talk, Shishuo. So any questions for him?
I'm sorry, maybe it's too much details to digest.
Hi, I have a question. So this is Arvind.
Hi.
Very nice talk. I just wanted to ask, were you able to generalize your results to hills of where your peaks were at higher heights, like going up to some height K and coming down, things like that?
Oh, you mean like other variants of shorter paths where you are allowed to go higher than one step?
Yeah. So I mean, your things went up to height 1 and came back, right? That's what you called a hill, right?
Yes.
I mean, does it generalize in a natural way? Do you still get reorder arrays and things like that?
Yeah, that seems interesting thing to think about. That we haven't thought, because once we were done with the first paper, we sort of shifted our focus to the permutation side.
Okay.
To the separable permutation side. Yeah. So after that, we did everything on the permutation and some with the discrete tree model. but we didn't think further with the shorter path model. Yeah, but thank you for the interesting remark. Yeah.
But you think it will still be given by some Riordan arrays, or if you take higher heights coming down?
Yes, I think if you refine it in the same way, like once you have this path, you put your refinement according to the number of hills. But now the hills, like you said, will be not going one unit step. It will be like going higher, allowed to be going higher. Yeah,
Right.
I think that could be done. Yeah, but of course you should have once you have to try something in this direction, at least you should have some numerical data support your result. Yeah, you have to see if there are really recurrences like this going on.
Right. Yeah. Sure. Yeah. Okay. Thanks. Nice.
Thank you.
Any other question from anyone?
Yes. Could you also?
Hi, Michael.
Hi. Could you also refine your Schroeder paths according to the bounce steps, or like a number of bounce points? I meant.
Number of bounce points, huh?
Yes.
Number of bounce.
Does it make sense? Because
What is bounce point?
I think it does make sense.
The number of points which meets the X line. Okay. The bottom line.
Yes, because I guess there was this bounce statistic originates from this so-called delta conjecture, right? There was a shorter version of this delta conjecture. This delta conjecture was mainly referring to this Catalan family, right? But I think there was a shorter version of it. So in that case, I guess there should be a corresponding bounce statistic corresponding to the shorter path.
Because in our joint work, we noticed that there's a relation between the hills, or maybe not the hills, but the area on the first level and the last bounce point, I think. I mean,
like similar, so like symmetry without
like symmetries, yeah, something like that, or well, anyway, I can write to you, and I can ask you more detailed, and we can
please
sort it out.
Yeah, I think that's definitely something interesting to think about. Yeah, connecting with the bounce statistic. Yeah, thank you.
Welcome.
If there are no further questions, let's unmute ourselves and clap for Shishuo for this nice talk.